Arduino, or really any programming language, can always be extended with libraries. They provide more functionality that would otherwise not be available to the user. In this video, we'll be talking about a number of common libraries for Arduino and go over a couple of them in detail. So, what exactly is a library? Well, it's really just a collection of pre written code that can be referenced or linked in a program. The idea here is you don't need to reinvent the wheel, somebody's already done the work for you. They provide ready-made functions, hardware support, communications tools such as, protocol support, and they can simplify interfaces for electronics. When it comes to Arduino, they're really subdivided into three categories: the official ones provided by Arduino, third-party libraries, and custom ones that can be made with the user. Yes, you can make your own custom libraries and you can even distribute them. Now, Arduino is a simplified dialect of C++, so libraries are in individual header files with the .h file type. They are included, linked into the main sketch by use of the hashtag include declaration. The libraries are linked to the main sketch and they're compiled with it. The libraries have to also be included in memory, so they take up even more space. This means that you should only include libraries when they're absolutely necessary for your program. Don't just include them willy-nilly. Compile code simply inserts the library bits into the main sketch, just like it inserts actual values when you use constants. There are about 150 to 200 official libraries. That sounds like a lot, but compare it to the 8 to 10,000 third-party ones that are just for the Arduino Uno Rev 3 alone. Now, third parties may also be providing better, newer, more efficient options to the official library counterparts, such as the Software Serial Library has a number of better third-party counterparts. So how do libraries and the Arduino IDE work? Well, one of the main function of the IDE is library management. You can search, download, install libraries from a number of sources. You can also add additional source URLs for even more libraries. Libraries are also used for board support. You have to make sure to install libraries for whatever dev board you're actually using with the IDE. And in fact, there may actually be even several options. If you don't include the correct include declaration for library, it'll give you a bunch of errors, not recognizing function names, certain variables, constants. It very rarely will just tell you, hey, you should have included the library. This is a big source of errors, confusion, especially among beginners. As I said, error messages are not clear. They can't generally infer what you did wrong, especially when it comes to not including libraries or not including the right library. A more old-fashioned approach to the ID would have required you to copy library files into a directory, include information about linking them during compiling. So how does this differ from using Walkaway? Well, it has a library manager too, but a number of the basic official libraries are already preloaded since it's not dealing with limited resources in quite the same way. You still have to include the include declaration in the sketch, check the library manager to see if the library is included in the list. If not, it might already just be included by default, although not every single library is supported on Walkaway for one reason or another. It might be because the associated component is not there, or it might be some kind of engine limitation. As I mentioned, the most common errors I see on Walkly in terms of questions from new users tends to be either basic program structure, like they have two setups, three loops, or something else entirely, or issues where they're not including the proper include or including the right library with library manager. I would say this accounts for easily a quarter of the errors that we run into. Now, here's a list of some pretty common Arduino libraries. People might argue with some of these choices, but you've got Wire, that's used for I2C, SPI, that's SPI, EEPROM, that's just entirely for the internal EEPROM. This has nothing to do with using external EEPROMs. Servo, that's used for servo motors. There tends to be a micro servo motor included in every hobby kit. Liquid crystal, that's used for certain kinds of LCD screens. More specific ones may have additional libraries or different libraries entirely. Software serial, that's where you want to do your software-based UART because you have very limited UART options with the Uno Rev 3. One wire, that's one wire protocol, mostly used with one particular temperature sensor, but there may be others. Adafruit has a bunch of libraries. There's a unified sensor one. It's a library that includes a bunch of different Adafruit sensors. DHT, that's used for the DHT 11 and 22. There's a bunch of small OLED screen libraries. I've just kind of included one. Um, and then Adafruit for drawing graphics on things like the SS 1306, other OLED screens. So in that case, one would be for interfacing, one would be for drawing actual graphics as opposed to text. iRemote, that's just for our infrared signal stuff. You've got HX711, that's load cells for like building digital skills. Cell stepper, that's for stepper motors. ST for writing and reading to SD cards via SPI. The good thing about it is the SPI stuff is built directly into that library. For Meta, that's for if you want to control Arduino with external software, Python processing, etc. There's plenty of others, but I wasn't going to spend 20 slides going over them. But this is a pretty good list of stuff you'll encounter in early tutorials. The first library I want to talk about is Wire. And this I've listed out the commands you basically use: begin, start up the process. This will set the Arduino or the device up to as master controller, and then end just ends the process. You don't really see end used much. Really, it depends if you need to turn on and off the I2C process, and then you begin transmission to a given device. You can also use in transmission. The good thing about in transmission is it'll throw code. If it throws a zero, it's working perfectly fine. If it throws something else, it's one of number of error codes. Using both together is a great way to make sure you can not only transmit um, but you know what who you're starting the transmission with. Um, if you have a bus with multiple devices, obviously you're going to have to begin and end transmissions back and forth. You can write a single byte to your transmission target, or in response to a request for data. You can set clock if you want. The default is 100K. I think in most instances this works. However, you may have a device that can't do 100K, or maybe you want to try for something higher. Um, now, yeah, so we could do a request too. Um, Number of bytes from an address. We can also set it to completely stop and release the bus after that request. When we're dealing with just two things like the Arduino and one device, a lot of this isn't necessary. When we develop a multi-device bus, this becomes more necessary. We can check to see if data is available. We can read the next byte. We have thing known as handlers, on receive, on request. We can set up, we can basically tell, well, when we get a receive or request, do these functions. We can set timeouts and timeout flags and stuff. This is basically if we reach a timeout event where something just hasn't happened within a certain amount of time, it'll put a flag up telling us this has happened, and we can check that, but then we can also clear that. Keep in mind the wire library has a maximum buffer of only 32 bytes. For a lot of I2C stuff, that's fine, but just keep in mind, don't try to send it a whole ton of stuff at once. One, maybe a couple of bytes. I couldn't tell you what the highest amount I've ever sent, but everything has to fit within that buffer. All right, we've got SimU IDE up. I've got two Unos, since I think this is one of the only ways I know to actually simulate two Unos. We've got two different sketches. We're going to have one, the one on the left acts as a controller, the one on the right act as a peripheral, showing off a couple of different functions. I've got a logic analyzer hooked up, but ignore that for the moment. So the first sketch, we're going to set the address here as a constant because, you know, that's never going to change. On the peripheral, we've basically got the same thing. So the peripheral is saying this is my address. The controller is saying this is the peripheral's address. All right, so they all agree. We're starting up a serial on both sides. Yeah, serial on both sides. We're beginning wire beginning here because this first one's going to act as a controller. On the other one, it's going to begin and it's going to begin at this address. We don't need the controller's address though. We just need the peripheral's address. So that's the difference in the beginning there. We're saying, here's the beginning of the demo, yada, yada. Um, we've got functions set up here for send data to peripheral and read data from peripheral. So send data, it's going to begin transmission. We've specifying the address here. We're going to write hello as a string, and then we're going to also send a single byte. On the other side, we've got two handlers set up, as I've mentioned, on receive and on request. So when it gets data, it's going to do this. When there's a request for data, it's going to do this, which the request is not really doing much of anything. So it's going to write hello and whatever. It's going to say receive. It's going to check to see what's on the wire here available. It's just going to read it in character by character and it's going to print it. It's pretty simple. And then it's going to just do a new line down here. And then if it actually gets request data, it's just going to write something back. I could write anything I want, to be honest. I just threw something in. This was actually some pre-existing code that I just modified, to be honest. So once it's done that, it ends transmission. That way it frees up the line. It says that it's in the transmission. Now, if it reaches a point here, and it didn't do it at the beginning, but if nothing works, then it eventually ends transmission. So let's just say all of this didn't do anything. Well, we're actually looking at a result here from when we end transmission. It's still doing the transmission. If it's a 0, that's great, success. If it's an error 1, buffer overflow. We're trying to push too much through the buffer. Address is not acknowledged, data is not acknowledged, some kind of other error. Can't recall ever seeing error 4. And then the default is unknown if it coughs up some other number, which it shouldn't. I mean, I've seen errors 1, 2, and 3 before. I don't think I've ever seen 4, and I don't think I've ever seen any other kind of number, but it's there. If we're going to read back data, which it's only one little thing that it's going to send back. In this case, reading for peripheral, we're setting a variable requesting 8 bytes. We're going to request the address, and we're going to request 8 bytes of information here. And it's going to just write it in, which I believe, let's see, 2, 3, 7, I guess, but I think something else in there makes it 8, but whatever. 7, 8, uh, close enough. The buffer is 32. So as long as it's 32 or under, we're fine. Okay, well, let's see what happens when we run this. This is going to be in a loop, as you've noticed on the first thing here. So it's going to send data, wait a second, read data, wait 3 seconds, rinse and repeat. Okay, it's doing stuff. Well, let's look at the logic analyzer first. So we've got our clock on the top. Now remember that it's got to do everything with the clock. Now we haven't gotten into too much in depth on I2C yet. That will be a future video. In this case, I'm not really focusing on the hardware. I'm just focusing on the library. All right. Well, let's look at the monitors here. All right, so it's definitely doing stuff. These are the watchdogs. We're not using those. RAM. So it's definitely moving data in and out around the RAM. Flash, it's not writing anything. It's just reading the program. We're not doing anything with the EEPROM. I couldn't tell you each of these status things up here. Maybe I'll make a future video. All right. All right. Well, let's look at the other one. So it's doing stuff not as much, and it's doing different stuff. So RAM, but again, it's not doing as much as the first one. Hey, here's our little message there. Um, And then flash memory, it's reading the program. We're doing nothing with EEPROM. All right. And the status here is it's really, IHZ, but it's not really doing much. All right, well, let's look at since we know we're doing stuff to serial monitor, let's take a look. All right, well, there's the first serial monitor. Here is the second serial monitor, just to show that something different is happening. So what's exactly happening here? Well, it's writing, it's saying that it's received hello you, which is what it's sending. And then this is receiving 8 bytes of Uno. Yeah, okay, so the final eighth byte is just a space. Even though the message doesn't show it in, that's just part of serial. So yeah, transmitting back and forth here. Each time it's a success because there's no mistakes. Let's see what happens if it something. Let's play around here. All right, you know what? Let's take off a wire. Let's see what happens when my messages we're gonna get there. All right, see, we're getting an ACK failure in this case. So we're not getting address that the line's broken. So this gives us a very helpful error message. All right, well, let's see what happens with the other one. Let's move 4 back on the line. Okay, there's 4. Well, let's remove the other one. Okay, let's see what messages it coughs up here. All right, we're still getting the same NAC because we're missing the other line. In terms of data, I'm not sure. It'd probably have to be something screwed up in the sketch in that case. Well, actually, something screwed up in the sketch could work either way. All right. All right. Everything's reconnected. Let's see what it says now. Yeah, we're all good. Success. We're getting messages back and forth again. So, yep. So that's basically I2C. It's not including literally every single thing you can do in Wire, but it's including all the important stuff, including the handlers over here. And then we have SPI. There's more complexity to this. You can set up SPI settings as an object. Originally, you would use particular functions. This is depreciated. Still works, but you'll see it in old Arduino sketches. Better just use the object method. You set max speed, your data order, which is lowest significant byte or most significant byte. And your data mode, if you remember from earlier videos, there's 4 different data modes that SPI can work on. Mode 0 is probably the safest. You begin, it just initializes the bus, it sets up the Arduino as a controller master in, disables it, pretty simple. Begin transaction, it sets up the bus, configures it. This is not the same as initializing it, and then you can end transaction. Basically, the transaction puts the Arduino in exclusive control over the bus, and then if you need to end it, you can end it. Um, and then using interrupt basically basically modifies an interrupt service request so that begin transaction disables it so that the actual transaction can't be interrupted, and then you just use in transaction to re-enable it. So if you're dealing with interrupt service requests, you might want to look into using that function. Transfer, it just sends and receive data of 1 bit, and then there's transfer 16 that does 1 byte and 2 bytes. Keep in mind, SPI is full duplex. It's going to send and receive at the same time. If it has nothing to receive, then it has nothing to receive. That's not an issue. And I already mentioned depreciated functions. As I said, there's a lot less functions, but there's a lot more built into them with SPI. All right, here we're looking at SPI with 2 Unos. On the left, we've got the controller sketch. We set our chip select pin right here. We're setting a counter, which is going to go up every time we do a loop. We're setting up our serial monitor. We're setting our chip select pin to output. We are setting it to high. Yeah, this is basically going to control kind of what when we're going to actually transfer. This is when we're going to flip that pin. So we're beginning SPI, pretty simple here. On the peripheral side, we're beginning serial. We're setting our chip select. In this case, it's just 12. This is short, so I kept it. And then we're actually going to manipulate the hardware register directly. This just made things a little bit easier. And we're setting that initial register, setting that to 0, and we're setting everything into peripheral mode. Oh, I must have put slave mode there. But at any rate, so on the controller side, we're setting the initial transaction with SPI settings. I think this is 1 megahertz, most significant bit first, SPI mode 0. We're taking the pin low. We're doing a transfer of the count. So the count's 0, 1, 2, 3, whatever. Um, we're writing the pin high. We're ending the transaction. We're saying what we sent. We're saying what we received. Keep in mind, this is SPI. It's full duplex. On the peripheral side of things, we tried to see if a transfer has actually happened. If it has, then we set our receive here. Receive it back. Well, let's see how this all works. Actually, it's pretty simple. Clear this out. Let me set the other one here. Oh, let's clear that out. All right, let's run it and see what happens. Okay, this sends, this receives, and then that register is immediately altered so that it's 100 plus, whatever this was. That's just to show that it's sending and receiving all at the same time over the same lines. And it's just going to keep counting infinitely here. And then we've got EEPROM. This is pretty simple. You're just dealing with the internal EEPROM. You can read a byte at the time. You can write a value. You can read from specific address. Again, it's a byte. Um, Get version does this by reference instead of value. Write, same idea. Update does it, but only if different. Put does this, but reference by instead of value. You can treat EEPROM as an array too, so that you can directly write or read to individual cells that way. You can also use length to get the number of cells in EEPROM. Keep in mind on the Atmega 328, it probably has about 100,000 write array cycles. Use them wisely, but keep in mind that chip can technically be ordered and replaced on a non-surface mount board. Uh, for basic experimentation, as long as you're being good about it, 100,000 isn't too bad. The big two things is don't put writes into a loop. Use update when needed. Don't you again use update except when you have to use write, because otherwise it could be writing the same thing over and over again, and it could literally use up that 100,000 within milliseconds if you're not careful. So use this with extreme caution. All right, here is using the library for EEPROM. We're setting up a data structure up here. We're setting up our serial monitor. Uh, Going with saying EEPROM demo, etc. The first thing we're doing, since we're using the EEPROM object here, we're printing out its length. See the size. We're reading address 0. Actually, no, excuse me. We're writing first. 123 at 0. We're reading that. Doing an update, keep in mind it's only going to do the update unless the value is different, and the value is different. We're reading again. Okay, the value's been updated. Keep in mind this means 2 write cycles so far. We're writing a whole structure here. We're using put to put it in. Um, we're putting it in at address 10, or starting it at address 10 anyways. We're reading it back with get. And then now we're just gonna go through the first 20 bytes of EEPROM. So we've done about a bunch of writing here. Not sure if this counts as just one write cycle or not, but at least 3 write cycles. Going through at 0, we have that 210, we have that 42, but 11 at 0. I don't remember precisely where everything ends. Let's see, it would be, let's see, I think int, no, actually int would be a couple bytes, 4. So I think it would be 4, 4, well, something like that. Um, but yeah, pretty easy to use the internal EEPROM. Then we have servo that's used for servo motors. You're probably going to have a servo micro servo motor anyway in your kit. You attach it to a particular pin. You can also set min and max pulse width. Attach will just check to see if it's attached to a pin. Detaches removes the servo from that its pin so that you can use that pin for other things. Right is an angle between 0 and 180. If it happens to be continuous rotation servo, it's just going to set the rate of rotation, so know the difference. I'm going to cover motors and servo motors in later videos. There's also right milliseconds that sets rotation in milliseconds. Keep in mind with this command, individual motors may function differently with different values. The library technically allows up to 12 servos to use a single timer. This is going to be more feasible with things like the Omega. Also keep in mind the library disables analog write on pins 9 and 10, regardless if you're using those. Apparently this doesn't apply to the Mega. Some different dev boards, different rules for how this all works. All right, let's look at a quick servo example. We turn it on, it's just going to sweep from one side to the other like it's supposed to. Let's stop it, let's look at it. Whose library? It sets up a servo object called myServo. It sets the initial servo position. It's not actually at 0, but ignore that. It attaches it to a pin, which is going to be pin 9. We're going through a for loop. We're writing the position. We're changing the for loop, taking it from 0 to 180, and then adding 1 until we reach that. We're delaying 15 milliseconds between each one. We don't want to kill servo motor. Not that we can, this is a simulation. And then we're doing the opposite in the opposite direction, just going back and forth on a loop here. Not entirely sure. Let's see, you can do horns. I'm not sure if you can actually do terms or references. Okay, horns. I don't see an option for continuous servo, so I guess you can't. All right. All right, I thought I'd take a look at something a little more complicated in SimID. I wasn't able to compile inside, so I had to bring the code over. But anyways, yeah, including the library, setting up the object, attaching, writing, doing delay, writing again, reading what the angle is, listing off the current angle. Actually, let's see if we can bring up serial monitor. Let's do it again. Notice it's attached. It gives the current angle. It gives the current with pulse. Detaches, reattaches, detaches for 2 seconds, reattaches. Does in here, it does move it with a 1000 millisecond pulse instead, reads the pulses, tells us, does it again, and then it goes into a loop where it attaches. It moves it from 0 to 180, moves it from 180 to 0, detaches it, says it detaches for 2 seconds, reattaches it, and repeats. So this version does a lot more of the servo functions. And then we have a liquid crystal. This is going to really vary. I mean, not every LCD is going to work the same, but if one comes with your hobby kit, it could be this, or it could be a simpler I2C. You basically create your object. You begin. You can clear. You can set the cursor. You can put the cursor at home. Print data, or you could just write. You can turn the cursor on and off. You can blink it on or off. Keep in mind some specific displays will work a little bit differently with all of this. You can turn on and off the display. Turning off the display does not clear it. The data is still there. It's just not visible. Um, you can scroll display left, right, move it a space. You do auto scrolling on or off. It really depends whether or not the cursor moves or not, essentially. You can do it left to right or right to left. You can even create custom characters or glyphs. Keep in mind, specific display devices may give you different results with this library. There are also variant libraries, so a lot of these will include some kind of I2C interface chip to make everything simpler. Um, but you could, if you really want to, I guess you could unsolder it and use the direct wiring without an interface chip. This becomes harder to use, but there you go. All right, here's a lengthy example for a liquid crystal. So we're initializing the liquid crystal object up here. We're setting the pins, 6 of them. Let's see, what are we missing? Yeah, we're not using D1 through D3. Those are optional anyways. We're not using VO. I'm not entirely sure what that was, but this is the important 6. We're beginning it as 16 rows and 2 columns. Let's see what it does. Okay, a custom character. Oh, and it's just going to go through. So let's see. Clears, it sets the cursor at a particular position, it prints a message. It moves the cursor down 1 column, prints another message, waits 2 seconds. Clear, cursor, home test, goes back to home, prints home, so it actually puts home again. We test the cursor, turning it on and off, blinking on and off. Keep in mind, in real life with particular displays, the behavior that may be a little bit different. Turns on the display off and on. Obviously, it doesn't remove the stuff that's actually on it. It just turns the display off. Um, Scrolling text. We did a clear. We did a back. We did a left. Then we did a right. We did auto scrolling. We did characters and let it auto scroll. We turned off auto scroll. We made a custom character, a smiley here. Now you can find, if you want this, you can find online tools that'll help you make this instead of actually having to figure out all the numbers. We create the character, we set cursors, we did some more, and that's basically all the functions in Liquid Crystal display. Then we have software serial. This basically lets you set up software-based UART object support, um, because hardware UART is kind of limited, especially on the Uno. You just set your receive, send pins, and if you need to do inverse logic, like you don't want 0 to be a 0, you want it to be a 1, set up inverse logic. It's pretty simple, available to see the number of bytes on the available to the read. You can set the baud rate. You can see if it's listening. You can check if there's been an overflow issue. The buffer is 64 bytes max. You can peek, that doesn't take it off the buffer, that just looks at the next value, or you can use read and it will return it and then remove it from the buffer. Print, human readable text. Print line, adds a new line. Write, prints as raw data. Keep in mind this only operates at half duplex and it does fine enough at lower baud speeds. I usually start at 9600, and if I need faster, then I might inch it up there, but it might have difficulty at 115 to 100. Your mileage may vary. All right, now we have a little simple setup here with two Unos using serial, uh, software serial, sorry. I'm just keeping it really simple because a lot of the ideas from the UART um, examples I've done in other videos are about the same here. But I didn't give a UART example in this video because it doesn't use a special library. This does, obviously, so we pick two pins, we begin the link, we set up the object, we say that Uno 1 sender is ready. We send a message to the other thing saying hello from Uno 1. We print back set message to Uno B. On the other one, we simply say that Uno B receiver is ready. And then if there's any bytes in the link, we start printing off the string until we get to a new line, and then received. And here's Uno 1. There we go, running again. See, it's sent message. And the other one, we received the message, and there it's pretty simple. So just to wrap things up, a library is a collection of pre-written code be referenced by another program, and this avoids the user having to reinvent the wheel. They often provide support for hardware, communications, or just simplified interfaces. The library code is mixed into the main program when it's compiled or linked. Make sure to only include libraries that are needed for the program. A reminder about the limited resources of things like the Arduino Uno Rev 3, the Arduino IDE Walkway have a library manager. You'll need to include install libraries or else you'll get a lot of confusing errors. There's a lot of common Arduino libraries, mostly official, used in tutorials. I talked about there being 100 plus official ones and upwards of 10,000 third-party ones. We looked at a couple of them: Wire, SPI, SD, Servo, Software Serial, EEPROM, and Liquid Crystal. There are maybe third-party options for official libraries. They might be more capable, more modern, more efficient, or they may just be created for specific use cases. Well, until next time, have a good one.